So here we have this. Now, to find first what is across the x-axis is not an obvious question. So remember, where this thing crosses the x-axis, its y value is going to be 0. So that question is really asking us to see where it crosses the x-axis. We want to know where is it equal to 0. And so if you solve this, if we add b to the x to the other side, and we take the natural log of both sides, then we get that the natural log of 1, which of course we all remember is, because we got all of us, the natural log of 1 is actually 0. So this is, so if you, and another way of, I don't know if you remember your graph, maybe not. So e to the x is going to look something like that. The negative is going to reflect it in the x. So now this point that was at 0, 1 is at 1, 0. This is going to get moved up. So that we want, yeah, so it x equals 0. So it's going to be right at the origin. Okay, so this is going to, our curve is going to do something like this. It's going to go through the point 0, 0. So we want the slope when it crosses the x-axis. So slope, we know, is equal to the derivative evaluated at the point in question, which is going to be at x equals 0. Okay with that so far? So the derivative, first, prime of x. Well, the derivative of 1 is 0. The derivative of e to the x, remember, is our new favorite derivative. The derivative of e to the x is just e to the x. So the derivative of negative e to the x is going to be negative e to the x. Okay? And then we evaluate that at 0, and that's going to be negative e to the 0, which is going to be just negative 1. And then the tangent line, so the tangent line is going to be, we need a point on the slope. We just got the slope, and we said the point is 0, 0. So the equation of that line is going to be y equals negative x, and then that's also the y-intercept. So you'll just do negative x plus 0, or just y equals negative x is our tangent line. Okay? Now, a normal line is the line perpendicular to the tangent line at the point of tangency. So we're still at the same point, 0, 0. And now, if our slope is negative 1, the slope of the line perpendicular to that will be the negative reciprocal, which is going to be then just positive 1. So it goes through the point 0, 0, slope 1, so the normal line is going to be x. So, and there's a visual going on here. So we have this, you know, this curve, this reflected exponential growth curve that was translated up 1. And it looks something like the orange there. So the tangent line right here is going to be this line that goes through the origin and has slope negative 1. And then the normal line is going to be, at that same point, is going to be perpendicular to the tangent line. So that's kind of the visual. I mean, you don't have to do all of that graphing and stuff, but that's the picture that's behind the scenes there. Anything else? Okay, well, this is going to be a good day. We're going to long last learn our product and quotient rule. So it may be surprising, but let me just convince you of what it is, or what it isn't, first of all. So if we say that f of x is x squared and g of x is x cubed, then if we look at the product of those two, so f of x times g of x is going to be x squared times x to the third. And I always hesitate to ask this question because I'm afraid of what the answer might be. What is x squared times x to the third? X to the fifth, right? so we can see clearly that the derivative, and I'm just going to write it as f times g to be efficient, in this case is going to be 5x to the 4th. Now, what understandably, what people want to do when they start out is say, well, shouldn't, and it's not going to work this way, shouldn't the derivative of f of x times g of x be, and I'm going to write big question marks there, shouldn't it be f prime of x times g prime of x? But it isn't. So we can see that because if we tried that in this case, we would say the derivative of f is going to be 2x, and the derivative of g is going to be 3x squared, and 2x times 3x squared is 6x cubed, and that's clearly not going to be the 5x to the 4th that we know it should be. Oh, this is perplexing. See the issue? So that is not the product rule for two functions. Instead, what it is I get to play conductor, something that is like always been a dream of mine. So in fact, what the derivative, the product rule, the derivative of f of x times g of x is the first times the derivative of the second plus the second times the derivative of the first. It is the first times the derivative of the second plus the second times the derivative of the first. Say it with me. The product rule is the first times the derivative of the second plus the second times the derivative of the first. The product rule is the first. It always works when I do it up on stage. It is the first times the derivative of the second plus the second times the derivative of the first. The product rule is the first times the derivative of the second plus the second times the derivative of the first. The product rule is the first. Thank you for helping me fulfill a lifetime goal of mine. Okay, so let's see why it really does work. So the first, in our case, we said the first is x squared. The derivative of the second is the derivative of x cubed, which is 3x squared. Now the second is the x cubed times the derivative of the first, and the derivative of x squared is 2x. And so when we simplify this, x squared times 3x squared is 3x to the 4th. And x cubed times 2x is 2x to the 4th. Now they're like terms. 3x to the 4th plus 2x to the 4th is indeed 5x to the 4th, which is what we needed it to be. I never did that. I erased it. So we know the derivative was 5x to the 4th. Okay, so that's just to make you believe it. Okay. Now I know it seems silly, but saying it out loud, at least initially, the first few days while you do it, and inside your head all the time, will help you remember it better. And if you think this is complicated, just wait till you see the quotient rule. It will make you better appreciate the product rule. So let's do something like, say, f of x is x squared e to the x. So now we have to start learning, training our brains how to see this as a product of two functions. And so that takes a little bit of practice. And then we're going to complicate matters tomorrow, because we're going to do the chain rule, which is a function inside a function. And so it can be easy to get confused when you're starting out to think that, one is the other, that the product of two is really a function inside the other, or a function inside another. F of g of x is f of x times g of x, and you got to be able to see and distinguish between those. But what is the first function here? x squared. Then what is the second function? E to the x. So we're going to take the first times the derivative of the second. I'll get this one. E to the x is e to the x. There's my contribution. Okay, plus the second times the derivative of the first, which is, we usually write that out in front, so it just looks better that way. And so there we have it. There is our product rule. Okay, let's do one. So sometimes you may get some artificially constructed ones now because we don't know very many different functions yet. That's about to change. We'll learn shortly how to differentiate all the different trig functions and so on. But for right now, it's going to be maybe a little bit artificial because we could certainly find this derivative without using the product rule. Because we could just multiply this stuff out, not that that would be very fun, and then take the derivative there. But we're going to do it using the product rule. And in this case, I'm not even going to simplify it. It's just the product rule that I'm trying to reinforce here. It's the calculus part, not the algebra. Not that algebra couldn't stand a little extra work. So we're going to take the first times the derivative of the second, which is 3, plus the second times the derivative of the first. And so tell me, what is the derivative of the first? And that's it, right? Because the derivative of 5 is 0. That's good for now. That's fine. Does that make sense? Okay. So that may have seemed complicated, but let's talk about the quotient rule. Talk about complicated. Okay, so we are now going to differentiate two functions that are being divided. You ready for this? Or ready or not? It is the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. So sometimes it can be written, I don't know if this is any help or not, but you could say it's the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. Some other people know I can never keep it straight because I'm not into these. You know, I don't sing my quadratic formula, even though I know a lot of you do. There's some high D, low D, I don't know. Like I said, I don't know. You have to look that up online. I don't know that way of doing it. All right, but I do know how to direct it. Are we ready for the quotient rule? Correct answer is yes. Okay, so it is going to be the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. The quotient rule is the denominator times the derivative of the numerator minus the numerator all over the denominator squared. The quotient rule is the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. The product rule is first times the derivative of the second plus the second times the derivative of the first. Oh, so complicated. Make sense? Sort of. All right. So let's do one. Let's say we have already in EDX notation. Try to use as many notations as we can. We'll do x squared over about the only other thing we know other than a polynomial, e to the x. So we have the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over denominator squared. The denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all of the denominator squared. We are going to clean this up. So in general, we'll bring this out in front. So we'll write it as 2x e to the x minus x squared e to the x. More exponent rules. E to the x raised to the second is e to the 2x. Very nice. Okay, there we go. All right, let's try another one. So we'll say f of x equals, let's say y equals, these are Leibniz notation, y equals x to the second minus 3x all over x plus 5. So we'll say dy dx. And we'll write our derivative. Okay, so we are going to get the denominator, that's dx plus 5, times the derivative of the numerator, which is, very nice, minus the numerator, 3x squared minus 3x, times the derivative of the denominator, which is just 1, all over the denominator squared. And in this case, I'm just going to stop here because there's not very much interesting simplification, but we'll, in the future, not too long, we'll get more complicated stuff, and there'll be some pretty serious algebra that will have to happen here, but we'll get to that. Now, because this quotient rule is so complex, we want to not use the quotient rule unless we really have to. So there are certain situations, and I want to talk about some of them, that you could certainly use the quotient rule, but that would not be the most efficient way to do it. So I will say be alert to avoiding the quotient rule when possible. Now, some people take this to, I think, a dangerous extreme, because you could, of course, once we learn about the chain rule, which we will do shortly, you could rewrite every division as a multiplication and just multiply and make that denominator into a product times that thing to the negative 1 power. I don't recommend that. I don't think that's a good strategy. I don't think not learning the quotient rule and never using the quotient rule is a good move. We will see there are times where it's going to be much better for what we're going to do with the derivative to have it written as a fraction and to always make it into some kind of first times derivative second plus second times derivative of the first. So these are going to be some examples of where we can avoid using and should avoid using the quotient rule. So one is if your denominator is just a plain number. So you could certainly do the quotient rule here, but that really wouldn't be very efficient given how long and arduous the quotient rule is. Better than that would be to do what? What is it? So yeah, you could either, one of two ways, you can either write it as 1/5 times this whole thing, because now it's a constant times a function, and so the derivative is going to be just a constant times the derivative of the function. Or alternatively, which would be the same, is you could, split this up and maybe write it as 1/5 x squared minus 3/5 x plus 5/5 is 1. Does that make sense how I did that? I need nods of heads. Katie, you okay with that? So one of these two forms is going to be the better way to go. I haven't done any calculus yet, so this is just kind of a little prep work in advance. Then we can say f prime of x, if we did it this way, we would say the derivative is going to be 2/5 x minus 3/5, and then we're done. And this way we would just say that f prime of x, we would just leave the 1/5, and then say the derivative of x squared is 2x, and the derivative of negative 3x is negative 3, and then probably either leave it like that or distribute the 1/5 through. So denominator a constant, don't use quotient rule. That's not an effective way of doing it. Okay, another thing that we will see, if you have something like, say, g of x is 2x cubed minus 7 all over x squared. So even when the denominator is not just a constant, but if the denominator is a monomial, if it's just one term, I don't think, I mean, you could certainly do, and it's some power of x or a number times the power of x. I'm not so sure this works as well if that's like e to the x or sine x or something like that. Then you might be just about the same place if you use quotient rule. But in this case, rather than doing the quotient rule, it's that same idea of splitting it apart. At least this is how I think of it. Now there's another way of doing this correctly as well. This is what goes on in my mind when I see this, is we're going to split this apart and simplify each one. Some people do the same thing by making this an x to the negative 2 and then distributing that x to the negative 2. Does that make sense? How these are doing the same thing? And so the way in my head I do this is we'll cancel that and just call it 2x. And then the 7 over x squared, I would call 7x to the negative 2 because that's a more derivative-friendly form than leaving it over x squared. Is that okay? And we get to the same place this way because when we add exponents, we're going to get 2x, and then there's our minus 7x to the negative 2. Now, we haven't done any calculus yet, but we're not going to use the quotient rule. Katie, you with me here? You try to blink on a regular basis. Good, so g prime of x, then, that derivative is going to be 2 minus 14x. Plus 14 sounds even better. Okay, is that all right? Okay, so let's look at this now. We've done this with derivatives as equations, and we still want to be able to do product and quotient rule when our functions are given as tables or as graphs. So let's see if we can explore that. So I'm going to give you, so this is now numerical representations of functions. So I'm going to give you a table, x and f of x and g of x and f prime of x and g prime of x. And I'm going to give you these values at a few selected values of x. So we're going to say at 2 and negative 3. So 2 and negative 3. And so we will get 5 and negative 4. I'm going, let me go across 5, negative 1, 2, and negative 6. And then the bottom row, 4, 3, 11, and 7. So there's our table of values. So we don't have equations for our functions f and g, so we can't actually try to do our way of finding the derivative, but we know the values where we need them. So let's find, we'll go first just a straightforward product rule. So we're going to take the derivative of f times g and evaluate that at x equals 2. Does that make sense what we're doing? Okay, I'll let you look ahead for a moment, and then I'm going to jump in. So see if you can do it on your own, but then I'll help you out. So we're going product rule. So we're thinking first times the derivative of the second plus the second times the derivative of the first. We evaluate everything there at 2. So that's going to be f of 2 times g prime of 2 plus g of 2 times times f prime of 2. Now we can go to our tables and read those off. F of 2 looks like 5. G prime of 2 is -6 plus G of 2 is -1 times F prime of 2 is 2. So it looks like -30 minus 2. I'm getting -32. Does that sound right? Make sense? Okay, so let's do, we'll just do a quotient rule. So let's find the derivative of, and let's take f of x over g of x, and we'll evaluate this one at -3. And I'll have to give you a quick graphing example. So we're going to get the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. So evaluating these all at x equals -3. You g of -3 times f prime of -3 minus f of -3 times g prime of -3 all of g of -3 squared. So g of -3, so 3, f prime of -3 is 11, f of -3 I think is -4, g prime of -3 is 7, all over g of -3 squared is going to be 3 squared. So I'm looking at 33 plus 28 over 9. However, if when I did the same thing, 50, 61 ninths, and I don't think that reduces. You okay with that? Did I go too fast?
Oh, I got it.
All right, we all right with that? Okay, I'm going to try you in 2 minutes here or less. Give you, same idea, but instead of the table, I'm going to give you the function of given as graph. So let's see what I can do. We've got, hold on a minute. I'm just going to be in quadrant 1. So we'll make this like this. So we'll go 1, 2, 3, 4, 1, 2, 3, 4, and 1, 2, 3, 4. F is going to be in pink, and F is going to go here. This is our f of x, and here, and here. So there's our f of x. G is going to be in green, so it's going to go to there, and all the way across to here, and then back up to there. There is our g of x. Okay, can we find, we'll say k of x is, say, g of x over f of x, and we want k prime, and we're going to evaluate that at, this is going to be very interesting. That's my g. Anyway, the idea is you can, we have a graph, you can tell what the value of the function is by its y-coordinates. And when these are straight line segments, its derivative is going to be the slope of that line segment there. So you can still evaluate it in that way. Does that make sense? There's an instructional support video if you want, and you need some more clarification where there's some of these worked out. Just a quick note before, if I can get you on the
coming to the counseling.
AP Classroom stuff, the one that needed a lockdown browser, I created a new one. It's on there today. So if you couldn't get it to work, don't do it. You can do it on there instead. If you did get the lockdown browser to work, and you did it, you don't have to do this one addition. But there is a second one also for today on what we did. So there's an old one going back to last week on 5 derivatives. There's a new one on product rule, quotient rule. Hope that makes sense.